Even Deepseek AI solved this problem. And can you? That's a question for you. Okay, the problem is limit n goes to infinity. Sum from k equals to 0 to n. And then binomial 2n choose 2k. And then this is Bernoulli number sub 2k divided by 2n to the power 2k. Right? So there's this new number involved called the Bernoulli number b, whose short intro I'll definitely give, right? This is nth Bernoulli number. But before that, let me show you that this has actually been solved by Deepseek AI. So as to make sure that you believe me, right? So yeah, I actually gave this problem to like Deepseek. He had the same problem, and it actually solved this problem, right? And the answer was, yeah, answer is 1 by e minus 1 plus half. You can also find the answer in terms of the hyperbolic cotangent function, but that does simplify it to the same answer. And so, yeah, that's interesting how AI is doing these stuffs. Yeah, basically, there's not a lot of things involved in this solution. So, yeah, maybe that's the reason it's solved. But yeah, definitely there are a few good formulas that DeepSeek used, and then we are going to discuss about those formulas in this video. But before that, let us try to use Bernoulli numbers. I'm going to do it in the really weird way, right? I'm going to make some new math conventions and some invents. I mean, do some like really weird things, and then yeah, we will get into the Bernoulli numbers. This can take around 5 minutes, and after that, we will go to the main solution of this problem. Okay, we know that. Let's say if I want to take an integral from let's say 0 to n, right? Of let's say x to the power some power m, right? Let's say if it's 3, then that's just x to the power 4 by 4 goes from 0 to n, right? And that's just become n to the power 4 by 4 minus 0. So that's just n to the power 4 by 4, right? Similarly, let's say instead of, sorry, I forgot the x over here. Instead of 3, if there's, let's say, some general power m, x to the power m dx, if I integrate it from 0 to n, that just becomes x to the power m plus 1 by m plus 1 from 0 to n. So that becomes n to the power m plus 1 by m plus 1 minus 0. So that becomes n to the power m plus 1 by m plus 1. Okay, so just like this, like if let's say if you want to find the sum of numbers, let's say from k equals to 0, this time up to n minus 1, and then we are basically dealing with k to the power m, let's say. Over here, basically the x variable was going from 0 to n. Now the k variable is going from 0 to n minus 1, and we are summing up k to the power m. And note that like short sums are really everywhere, right? Because let's say if m is 1, this 0 plus 1 plus 2 up to n minus 1, we have always like read this sum, right? This is basically n times n minus 1 by 2, right? Also sum of squares, sum of like cubes, first and natural numbers. We have done this. I mean, this is of some importance, right? So yeah, also there's a similar way to find this sum, right? So this will basically somewhat uh be a same expression just like the integral, right? So b plus x to the power just like the previous one, m plus 1 by m plus 1. And in this case, even though the sum is from 0 to n minus 1, the limits will be from 0 to n, right? And this will basically be b plus n to the power m plus 1 minus over here. I'm sorry for writing x over here. Actually, the variable is k in this case, right? It's k, and k is substituted by n in 0. So b plus 0 to the power m plus 1 by m plus 1, right? And so this is basically b plus n to the power m plus 1 minus b to the power m plus 1 by m plus 1. I haven't told you what b is till now, right? So again, now let us expand this b plus n to the power m plus 1. I will later on tell you. And while expanding, we will basically just assume that b to the power n will basically just be our nth Bernoulli number, right? This b to the power n will be our nth Bernoulli number. If we do that, what we get is over here, the first one will basically give us the following sum, right? Okay. So b to the power m plus 1. This will have m plus 1 to 0. But let me do a thing. What I will do is I will just see it in the reverse. I will just see it as n plus b, because that does do some simplification. So this now becomes m plus 1 to 0, and then that becomes n to the power, what does that become? So b sub m plus 1, right? Okay. Let me do it in the reverse way. So that means I will do b sub 0 n to the power m plus 1. It doesn't matter how I do it, right? And then m plus 1 choose 1. So basically this is b to the power 0, but I just defined that b to the power n be the nth Bernoulli number. That's some weird definition, but yeah, let's see how that works. And then b sub 1 n to the power m plus, now this will be m plus 1 choose 2, b sub 2 n to the power m minus 1, and then this goes in, right? Up to, on the last term is m plus 1, choose m plus 1, b sub m plus 1, and in this case n to the power 0, minus, now this is also b sub m plus 1 by m plus 1. Okay, and this is basically our sum from k equals to 0 to n minus 1, k to the power m. And sum from k equals to 0 to n minus 1 of k to the power m is now, yeah, notice that m plus 1 choose m plus 1 is just 1. So this n to the power 0 is just 1. So these last two terms basically cancel out. And so we have 1 by m plus 1, right? And then m plus 1 to 0, b sub 0, n to the power m plus 1, plus m plus 1 choose 1, b sub 1, n to the power m, plus m plus 1 choose 2, b sub 2, n to the power m minus 1. And then this goes up to m plus 1 choose m, b sub, that will be just m, because the last one is doesn't exist, and then there will be n to the power 1, right? And now the thing is, we have just defined this b to the power, like some power, just to be a Bernoulli number, right? And the most interesting thing is, no matter what the value of m is, m might be 1, 2, 3, anything, like these constants are always same. These constants are always the same numbers. And so that's why we are interested in defining these numbers as Bernoulli numbers, right? Let me show you, like now we know these numbers, like basically b sub 0 is just 1, b sub 1 is, I guess, minus half, b sub 2 is 1 over 6, b sub 3 is 0, and also all the odd Bernoulli numbers are 0. So b sub 5, b sub 7, all are 0. Now using this, let us try to see if this works. So yeah, sum from now, let's say k equals to 0 to n minus 1. Let's say if I want to find k to the power 1, this is just sum of first n minus 1 natural numbers. So that's just now becomes, using the same thing, uh b plus k to the power 2 over 2 from 0 to n, right? So and that becomes b plus n to the power 2. I'm substituting k as n minus b plus 0 square by 2. Now this is just b square n to the power 0 plus 2b n plus b to the power 0 and square by 2 minus b square by 2. Actually, b sub 0 is 1, so like it's just like b to the power 0 being 1. Yeah, that doesn't really matter. So now this is just b square plus 2bn plus n square minus b square by 2. B square cancels out. And now this b to the power 1 is just like b sub 1, right? N plus n square by 2. B sub 1 is just negative half. So this is minus half plus n square by 2. That means n times n minus 1 by 2. And that's exactly the sum of first n minus 1 natural numbers, right? If it was first n, then it would be n times n plus 1 by 2. But for first n minus 1, that's the formula. And it also works for any power of any n being any number. And yeah, so the fact that this b sub 1, b sub 2, b sub 3 are always the same numbers makes these numbers interesting, and so that's why we define these numbers. Okay, so now that we know where Bernoulli numbers are used, right, to find the sum of first and natural numbers, like to the power 2 or to the power 3 or to the any mth power, right? So yeah, so that's why Bernoulli numbers are defined. And later on, using the same definition and doing some modifications, people have come to know that this if we try to find the sum of this expression, this like Taylor series b to the power n by n factorial x to the power n, we actually get an expression which is just x by e to the power x minus 1. And that's an interesting like generating function to find the Bernoulli numbers, right? And yeah, also please do know that all the except b sub 1 except b sub 1, all b sub like 2n minus 1s are 0. And that's also an interesting observation about Bernoulli numbers, and you can prove this using some other definitions of Bernoulli numbers, right? Okay, now let us finally go into solving this problem. We will do the same way the Deepseek AI did, but we will discuss a bit more, right? So now we have limit n goes to infinity. What was the problem? And then yeah, sum from k is equals to 0 to n 2k b to the power 2k by 2n to the power 2k. Now notice that in this problem, n is going to infinity, right? N is like n's turning to infinity. Now for like when n's going to infinity, like there's an interesting formula for this binomial coefficient, right? And we are going to use that. So the thing is, if let's say n is really bigger than k, then this n sub k can be approximated by the formula n to the power k by k factorial. Yeah, and and if n is like really bigger, if n is almost infinity, this becomes a equality, right? And now if you want to prove this, you can actually use the Stirling's formula, like that approximates the n factorial, right? N factorial is equals to square root of 2 pi n by e to the power n, right? And for this, n should be really bigger. And if n is almost infinity, this becomes equality. So yeah, like now, if you want to prove this for the first formula using this Stirling's approximation formula, we can actually just break the n sub k, right? So we basically let's say our n is going to infinity. Now this becomes n factorial by k factorial n minus k factorial. Now there are two factorials involving n, and n is going to infinity, and k is just some number, right? So what I can do is use the formula 2 pi n by e to the power n. Similarly over here, there's the k factorial, and then square root of 2 pi n minus k, right? And then n minus k to the k by e to the power n minus. I'm sorry. Wait, let me manage this space. Let me manage this space over here. Okay, so square root of 2 pi n minus k by e to the power n minus k. Okay, so now after this, what you can do is limit n goes to infinity. You can basically cancel the square root of 2 pi from numerator and denominator, right? And that leaves us with n by n minus k, right? And then over here, what you can also do is uh like now like distribute the division among each of the exponents, right? So n to the power n by e to the power n minus k to the power n minus k by e to the power n minus k. Wait. I'm sorry. Actually, in the denominator, there's n minus k to the power n minus k. In numerator, there's e to the power n minus k, right? After that, limit n goes to infinity, 1 by k factorial. You can now write it as 1 by 1 minus k by n. And then now this just becomes 1 by e to the power k, right? We can just cancel the exponents. Now you can write this as n by n minus k to the power n, and then after that n minus k to the power k, right? Yeah, I think I'm right. So after that, limit n goes to infinity, 1 by k factorial. This is just 1 by 1 minus k by n. And now there's 1 by e to the power k. Also, you can write it as 1 by 1 minus k by n, and to the power n, also over here also to the power n, right? And also you can write this as n minus k by n to the power k times n to the power k, right? Okay. So now you can basically see what I'm trying to do. So first one is just 1 by k factorial. Second one is just 1 by 1 minus 0. And there's this 1 by e to the power k. And then now this is 1 by, we know that 1 minus k by n to the power n, when n is going to infinity, is just e to the power minus k. And now this one is just basically 1 minus k by infinity, right? So that's just 0 to the power k and then n to the power k. So from here we see that this eventually becomes n to the power k by k factorial. So yeah, so we see that when n's going to infinity, that means when n's really bigger than k, you can approximate binomial n's of k using the formula n to the power k by k factorial, right? So we are going to use that. So but here, since n is going to infinity, I can basically use that formula. So yeah, and also like I cannot actually do the limit like part by part. I need to do all it at once. But yeah, like doesn't really matter. So yeah, 0 to n. This is just 2n to the power 2k by 2k factorial, and then b sub 2k by 2n to the power 2k, right? Now we see that this cancels out. And then now we have this limit n goes to infinity, sum from k equals to 0 to n b sub 2k by 2k factorial. So basically this is same as, since n is going to infinity, basically we want to sum from 0 to infinity of the even Bernoulli numbers, right? Now I already told you that like the Bernoulli numbers, uh like there's a generating function for them, right? So this is x by e to the power x minus 1. So this is basically equals to the sum of the Bernoulli numbers divided by k factorial x to the power k, right? Now we also know that like all Bernoulli numbers are basically 0, and only the b sub 1 is the only Bernoulli number like that. uh that's basically an odd Bernoulli number. I mean, Bernoulli number with odd base, that's not 0. So what you can do is, if you just subtract that term involving x to the power 1 or involving b sub 1, then the only term, the all the terms left in this sum will be even, right? So yeah, that's what we are trying to do. So what I will do is, if we just isolate this b sub 1 by 1 factorial x to the power k, now since all the odd terms are actually 0, this is same as writing k to the power k equals to 0 to infinity b sub 2k by 2k factorial x to the power k, sorry, x to the power 2k, right? Because now since all the Bernoulli or odd Bernoulli terms go to 0, so that's just like effectively 0. So only even terms are required. Now we know that the b sub 1 is actually negative half, right? So using that, x by e to the power x minus 1, and sorry, and now this k was actually 1 in this case, right? So negative half of x plus sum from k equals to 0 to infinity b sub 2k by 2k factorial x to the power 2k. Now just take minus x by 2 to other side. That becomes x by e to the power x minus 1 plus x by 2 is equals to sum from k equals to 0 to infinity b sub 2k by 2k factorial x to the power 2k. And now if you want to find this sum, we just need to substitute x as 1, right? If you substitute x as 1, we get 1 by e minus 1 plus 1 by 2, which is sum from k equals to 0 to infinity b sub 2k by 2k factorial. And that's the answer, guys. That's a beautiful answer. Also, you can try to express this in terms of the hyperbolic cotangent. How you can do that is, okay, so for hyperbolic cotangent, you basically need this form, right? We know that cotangent of x is e to the power x plus e to the power minus x by e to the power x minus e to the power minus x, right? So maybe what you can do is, I'm not sure if that will work. So yeah, first of all, let us just try to make denominator in that form. I'm not even sure how to do that. Okay, let me see. Did you see the answer that one of my friend gave on the YouTube? So we'll try to like change cotangent to this form instead of doing the other way. Okay, so this is basically equals to the half of cotangent of half, right? So now we know that this can be written as e to the power half plus e to the power minus half by e to the power half minus e to the power minus half. Now this can again be written as e plus 1 by e minus 1. Now you can write that as half and then e minus 1 plus 2 by e minus 1. And now that becomes half 1 plus 2 by e minus 1. And now if you distribute this, half plus 1 by e minus 1. So that's basically the same thing, right? So yeah, this is basically the answer, both of them. And yeah, now this is, what was it? 1 by e minus 1, 1 plus half. 1 by e minus 1 plus half, or half of cotangent half. So that's the answer, guys. And yeah, that solves the problem. So that was an interesting problem. And yeah, I hope you here have seen that how AIs are getting really powerful these days, solving such problems using powerful theorems, right? And yeah, definitely. Like now, this is the time to collaborate with AI to discover new things, right? Not just human, but human and AI collaboratively can find new things. So definitely explore and learn and always be curious. So that's it for today, and look forward to seeing you in the upcoming video.